In this lecture, we will learn about electric field lines. Electrostatic is a branch of physics that studies electric charges at rest. And since classical physics, we know this, that some materials such as amber attract lightweight particles after rubbing. So electrostatic charges are there, and how electrostatic charges create the field and field lines we will discuss here. In this lecture, we will be able to learn what are electric field lines, why it needed, and what this electric field line represents, significance, and rules for drawing lines for single and multiple charges. Before going to understand the electric field, you must know from where this electric field is arising. This electric field is due to electrostatic charges. And yes, the electrostatic charges was first came into picture in classical physics by the materials like amber. And these charges created by rubbing. The electrostatic phenomena arise from these forces on the charges exert each other, and such forces are described by Coulomb's law. Coulomb's law was the first law who talked about force between the charges. And we know that according to Coulomb's law, the force between the two charges is proportional to their products of charge and inversely proportional to their distance. From these charges, we have developed a new term that is called electric field. The electric field is defined by E, and it is defined everywhere except the location of point charge, defined as the electrostatic force in Newton on hypothetical test charge. Actually, whenever we want to calculate electric field, we assume a test charge and we bring the test charge in a region and we assume the force on that charge. So the electric field is defined as force per unit charges. So F upon Q we define. But electric field is always represented in terms of electric field lines. And that is the thing that we want to discuss here today. The electric field lines are useful for visualizing the electric field. The electric field lines directly gives the idea quantity of charge on source charge and inversely proportional to distance from the source charge. Now as I told you that electric field is represented in terms of field lines. The number of field lines also known as lines of force, and this is related to strength of electric field. More appropriately, it is the number of field lines crossing a given surface related to electric field. The direction of electric field is always directed in the direction that a positive charge would be pushed or pulled if placed in space surrounding the source charge. There are some convention we are using here. Whenever we word use for test charge, whenever we want to check the field, we always use a concept of positive charge, test charge, and that test charge we always consider as positive. So the field line can be calculated on that. The electric field is a vector quantity and represented by vector arrow. As it is shown in the figure, for any given location, the arrow point in the direction of electric field, and their length is also proportional to length of electric field at that location. Try to see from here that here we have shown here the electric field vector for location around a negative and positive source charge. On the right hand side we have taken positive. That is why all the arrows are up outward direction. You can see these arrows are in outward direction, like this, like this. Also mention here the length. Length is more means strength is more, length is small means strength is small. Similarly, for negative charge, is moved towards, if the uh, as we close to the charge, source charge, then the strength is highest. So here you can have you can represent many vector arrows. But as you move away from the source charge, the strength decreases. So you can use less. But rather than draw countless vectors, arrows in space surrounding a source charge, normally it is useful to draw a pattern of several lines that extend between infinity and source charge. These lines or patterns, sometimes referred as electric field lines, and this point in the direction that a positive charge would accelerate if placed upon the line. So the important thing is the lines moves from the positive. If your source is positive, the line would be in outward direction, or if you are having negative, then it will be inward direction. These electric field lines, as we have told in the previous slide, then the source charge can be represented by electric field lines the field can be represented by electric field lines. These lines are directed away from the positive charge source, and for negative charge it is towards negative charge source, away from positive and towards negative. To communicate information about direction of the field, each line must include an arrowhead that point in appropriate direction. So just by viewing the arrows, you can check what charge is there, whether it's positive or negative. An electric field line pattern could include an infinite number of lines because drawing such large quantity of lines tends to decrease the readability of patterns. The number of lines is usually limited. We have to limit the lines. The presence of few lines around a charge is typically sufficient to convey the nature. There is no need to crowd the lines. Even a small lines can give the nature of the source. Let us see these three uh, sources. Can you say something about this? The first figure, this is shown that the arrows, just watch the arrows. Arrows in outward direction. If the arrows are in outward direction, it means this charge is positive. So this is shown, all the arrows are in outward direction. We are showing here positive charge. See the second figure. Here, see concentrate on any arrow. The arrow is in inward direction. All the directions, all the arrows are moving inward. The arrows are in inward direction. This shows that this is in negative charge. So in this way we can calculate positive and negative these sources. What about third? There is no inward or outward, so it is not a charge. Neutral. No charge. No positive, no negative. The electric field line patterns communicate information about nature of electric field surrounding a charged object. And as we saw in the last figures, that just by observing the lines, we can get the idea whether it is a positive or negative. Object with greater charge creates stronger magnetic field. Object with greater charge create stronger electric field. More lines represent strength more surrounding the object. However, in the last slide, we have not discussed anything on strength because in both the cases we have shown same lines. If lines are closer, then we can say strength is more. This can also be used to see the presence of your source, where the source is. When you are moving towards the source, the strength will increasing. So it should be represented by more lines. As you move away from the source, the number of lines is decreasing. Now the strength can be seen here. The density of electric field line around these objects reveals the quantity of charge C is greater than B or A. How I'm saying this? And C is greater than B and A? Yes, by observing the density of lines. The pattern you are observing, this pattern is less dense than this and than this. So if you are talking about density or strength, then this is most highest, then this is. So this gives a idea of strength also. This can be checked. We can also see one important thing here. Then when you are close to the source charge, the electric field lines are closer. And as you away from the source charge, the electric field lines become further and further. So the density of lines surrounding any object reveal information about the quantity of charge on the source and the strength of field at that location. Cross section represents the region of space closer to and further from the source charge. The field lines are closer together in the region of space close to the charge, and they are spread further as you move away. So this is also shows not only the number of line density is giving you the idea, but it also gives the idea whether you are close to the source or away from the source. The electric force and thus the electric field is always directed perpendicular to surface of the object. This is the conclusion. We must know that the field is always directed perpendicular to the surface of object. As far as we have developed first few rules. First is the electric field line always pointed outward from the positive charge inward to the negative charge. It also gives the idea of strength. Density of the number of lines gives the idea of strength. Then the electric field lines always is perpendicular to the surface. Now these field lines never cross each other, and it is also obvious if the two lines cross each other, then this will give you two directions of field, which is not possible. We know this, and the electric field is always have one direction at one place. So two distinct values of electric field is not possible. That is why we should know always that electric field lines never cross each other. Every single location in space has its own electric field strength and direction opposite associated with it. Consequently, the lines representing the field cannot cross each other. Now, talk about more than two charges or two charges. Suppose you are having two charges at one place. Here in this case, we have shown here two positive charges. A and B are both are two positive charges. Two positive charge means away from the source. But since we have two charges, now the resultant will work at all the places. If you are talking about anything which is exactly in the center, then this will be opposite to each other. EB is opposite to B and this is opposite to it. Maybe cancel out and the center. If both are same, if both are opposite, then the point center, the cancellation point may be somewhere on the line. But as you move away from this, you observe different behavior, EB and EA. Similarly here, you can calculate the values here by observing different directions. Each charge creates its own electric field at any given location surrounding two charges. The strength of the electric field can be calculated using expression kq upon r square or d square. D is the distance. Since there are two charges, you can calculate this value of kq over d square by these two locations. Suppose the distance from A is dA and dB is dB, then you can calculate this and you can find out the resultant value. If we are having many charges, then the electric field always extends from a positive charge to negative charge and from a positive charge object to infinity or from infinity to negative charge. Electric field lines never cross each other. Electric field lines dance around object with greatest amount of charge, and at location where electric field lines meet the surface of an object, these are perpendicular. So we must know these general rules all the time. That and it can be applied for one charge, two charge, or many. Now I have shown here some examples. Suppose you have two charges close to each other and one is positive and one is negative. Then they form a dipole, that is called electric dipole. From positive, there is all the field signs are in outward direction. From negative, it's in inward direction. But in there is they form a closed loop here. So it form a dipole if they are close to each other. Now take this example. In this example, I have shown two same charges, same positive charges. If both are positive, then they always repel each other, and there is nothing here. Nothing is possible here. So they both are in the outward direction. We can draw electric field using these rules for many charges, many possibilities. Now here some examples are given for object with unequal amount of charge. Either first see here in the first. The amount of charge is not same, suppose, and this is weak charge, this is strong charge. So you will get this type of behavior. Similarly, what you can say about this? In the second, you are observing this left charge is weak. What about the third figure? In this third figure, we have two different charges, positive and negative both. But which is more, strength is more? Yes, this negative charge has more strength. Similarly here, you can say positive is more. So you can get the idea of whether which type of charge are present. Just see the arrows, and by density, you can get the idea of which is more powerful than other. Now I'm giving you one task. Observe these electric fields lying below for various configurations. In the first, 2A and B are given, then the second D is given, then EFG is given, and HIJ is given. Rank the object according to which has the greatest magnitude of electric charge, which is higher, which is lower. You just rank and also give the idea which is positive, which is not. This is your exercise. Do this. You can see this. This is the answer. B is less than A. Strength is less and less field lines are there as compared to A. So this is your B. Similarly here D is powerful than C. In the first case, A is positive, B is negative. In second case, again, D is positive, C is negative. What about EFG? EF from F, like the lines are going outside, so and from G is also moving outside and E is also moving outside. So all are positive. First thing. The second thing is weakest. We can share here that G is the weakest, then E, and then F, just by observing the density. What about this? Yes, I looks strongest, then H, then J, and all are no. I from I is moving down upward direction, so I is positive and J and H is negative. So these are the answer can be calculated. Thanks. Today we have discussed a very basic idea of electric fields. Thank you. We have discussed basic idea of electric field lines, and this will be helpful in understanding flux and Gauss law, as we will discuss later on. Practice many numericals and such type of questions on this for numericals for electric field and basic question on field lines. Thank you.